My first way of testing the strength of these parts really wasn't very good. It wasn't very accurate. All I was doing was hanging weights off the bar. So I'm trying to get something which is much more metered. So I'm trying to make an adapter for a torque wrench. So, as you can see here, I have mounted the actual part on the bench. It's held on with a 6mm bolt, which is a pretty standard fixing point. We've got a bit of a lean-to, so the weight is spread out over the table, and then we've got the end. This is actually the weakest part I could possibly make. This printed in about, I think less than 10 minutes to print this was. This is 5% infill, which is about as low as you can go, with a 0.8mm wall thickness. So that is incredibly flimsy, but I thought I'd try it anyway. So now what I'm going to do is I'm going to machine up an aluminium part that will slide over the end, and then hopefully I can get a torque wrench on it as well. You just saw me milling this little adapter on the mill. What it is on one end we've got a 17mm hex. That was a complete fluke. I just eyeballed it and it turned out to be a perfect 17mm socket, which is absolutely spot on. On the other side is this milled cutaway, which will slide into the actual test piece. So we'll be able to put this on the end, torque wrench, and then we'll be able to get a reading for all the material of how well these are and how strong they are compared to each other. This is less than 5% infill and a wall thickness of 0.8mm. If this does 1 Newton meter, I'll be surprised. It flexes in your hand, but you know, that's from what I was playing with my printer. Hang on, I'll bring you in just so you can see, and then we'll do this one, and then we'll start filming some proper materials. So PLA, the torque wrench only goes to 5 Newton meters. That's going to break on 5 Newton meters. You can see it fracturing. Let's try some other materials. That's better. Jesus. Shit. So now we need a baseline to compare this to. So we're doing the exact same test, but rather than obviously use the 3D printed, we're going to use this 4mm steel bar. It is 20mm by 4mm, so it's the same width, but obviously 4mm in thickness, which is, you know, what is a lot of bracketry and things are made out of. It's really tough. You can flex it with your hands, but you can't permanently bend it. But that's actually what you can do with a strong piece. This is ABS, so a strong build. I can't bend it. There's no way I can break it out of my hands. Let's go. What we got? 5, up to 7. That's 10. 13. That's really starting to bend and deform. So steel is more ductile than plastic, so it will deform before it goes. Let's try 15 Newton meters. And that's deforming right there. We're going to do the bolt crushing test. So what we've got here is torque wrench set up to 5 Newton meters. Let's see how we get on. 5, 6, 7. Oh, that is loads better. So we are we're using the big washers these times. These are just a couple I had in my drawer. So these are much larger washers on a strong build, and this is already way surpassed what everything else does. We're already at 12 Newton meters and it's not even flinching. 16, 17. I'm gonna have to get my bigger, I'm gonna have to get my bigger Allen key. Better setup. We're at 19 Newton meters. 21. Starting to deform. I can feel it crushing. I actually thought I could, the plastic was deforming and starting to stretch, but actually, in fact, the stainless steel bolts we've been using, it's actually started to pull the threads on the stainless steel bolt. You probably can't see the thread rate from there, but yeah, I can now no longer turn it onto there, and you can visibly see that it's started to pull the threads on the bolt. So actually, the plastic outperformed the stainless steel bolt. So what have I learned from breaking all these bits of plastic? Loads. But before I go into it, someone had a question about the environmental impact of all this plastic. It's actually not as bad as you think. All this plastic I use is 100% recycled that comes on the reel as the filament. It's all 100% recycled. This PETG, which I think I'm going to use, is exactly the same material which is in plastic water bottles. So actually it gets recycled from them. So PETG is a really good recyclable one. It's 100% recycled. Also, when I get to a kilogram of waste, that can be cut off filaments or even broken extruded parts already. They'll come and collect that kilogram and then they recycle it back into the product. So it's actually not bad at all. Everything here is from recycled and will be recycled. But apart from that, what did we learn from the strength side of things? Actually loads. So from really weak builds that are incredibly weak to builds that are incredibly strong. So we now learn which materials are better. This material, PETG, is definitely stronger than everything else. We also know that it's really good externally. It doesn't degrade in sunlight, heat, temperature. It's really resistant to it as well, which is brilliant. So I now know what material I'm going to use. We also learn that the build quality of how you build it is very, very important. In fact, I worked out that if you make them completely solid, it's actually not as strong as if they've got a membrane inside. So if they've got like a lattice or an infill pattern, it's actually stronger. It gives it a little bit of ductility. It allows it to move a little bit and flex, and that gives it a better overall strength, which is brilliant. And as you can see by the videos, this medium, what I class as a medium strength build, outperforms steel, which is unbelievable for a similar product and what I would use it for. So that's actually unbelievable. This bit was never going to happen in one take, was it? What we found out was the bolt strength for these, I can actually get it to a point that I'm happy with. It was my biggest worry when I first started to do it. This one actually broke at 6 or 7 Newton meters, which is nowhere near strong enough. But what I found out later was different materials, they have different strength between each layer. This one's really weak, whereas PETG is really, really strong, got really good bond between the layers, and that made an absolute massive difference. So with a small washer, even on the low and the high step, this still withstood, I think it was 14 and 15 Newton meters, which is good enough, but obviously you want it to way surpass what it's ever going to need. Probably 10 Newton meters is where it's ever going to be. So if you use a big washer, it then jumps straight up to 21 Newton meters, and then it stripped the thread on the stainless bolt. So we know that it's more than capable of taking the force of bolts, which is brilliant. So now we know it's strong in itself, and also it can take bolt strength as well, which is brilliant. So yeah, we've learned lots, and now that means we can make really cool, awesome parts like this. This is a part of a project I'm doing at the minute. So yeah, we're starting making production parts now. Anyway, I better get on with some actual work today.